it's Emily. This morning, some friends and I toured this really cool biology lab. At first, all of these test tubes, microscopes, cultures, and other instruments seemed pretty intimidating. But once biologist Dr. Parker explained what they're used for, it didn't seem quite so mysterious. Turns out, it's just like when you understand logarithms. Let me show you how our tour became another problem solved. We were surprised at how much math is actually used here in the lab. For instance, Dr. Parker said the bacteria cells in this petri dish will grow exponentially. More specifically, the cells are growing by a factor of 10 each hour.
How long until the sample reaches 1 million cells?
Good question, Sarah. And actually, we need to determine when this will grow to 5 million cells. Exponents will quickly answer your question. But for 5 million, it'll be easier to use logarithms.
Logarithms?
Oh yeah, I know they can seem a little mysterious until you understand what they're used for. Emily, you've brushed up on your math. Care to explain?
Sure. Let's take a look at this petri dish. We could use the exponential growth of our bacteria cells to help us better understand logs. We'll call the time we begin growing our sample hour 0 and start with a single bacterium. After the first hour, we would have 10 bacteria, and after the second, we would have 100 bacteria. Notice if this exponential pattern continues, we see there will be 1 million bacteria after 6 hours. But we don't see 5 million bacteria in the table. The table goes from 1 million to 10 million. To find 5 million, we will need to use logarithms. Let's use the answer to Sarah's question, 6 hours, to help us understand this problem. To answer Sarah's question, we need to know what power of 10 is required to produce 1 million. In this case, the exponent is 6. Without knowing it, we just used a logarithm. The logarithm gives us the exponent necessary to produce a desired result. Logarithms answer the question, what power of the base is required to produce the given value? In our example, the logarithm of 1 million base 10 is 6, and the notation looks like this. Here's another example. If we were asked to find the log base 3 of 81, we would ask the question, 3 raised to what power is 81? 3 times 3 times 3 times 3 is 81, or 3 raised to the 4th power equals 81. The exponent is 4. 4 is the logarithm of 81 when the base is 3.
Now that example was pretty easy to calculate. When things are a little more difficult, we should be able to estimate our answer.
Right. Let's try estimating the log base 10 of 820. First, ask yourself, 10 to what power is 820? It's not an easy answer, but you do know that 10 to the 2nd power equals 100, and 10 to the 3rd power equals 1000, right? So, log base 10 of 820 has to be between 2, which is too small, and 3, which is too big. The actual value is close to 2 91/100ths. Let's go back to the original question about when the bacteria will reach 5 million. Looking at the number of hours and bacteria in the table and graph, we see they are plotted as a logarithm. We can estimate the answer knowing that 10 to the 6th power is 1 million, that's too small, and 10 to the 7th power is 10 million, that's too big. So we know that log base 10 of 5 million is between 6 and 7. It turns out that in approximately 6 7/10 hours, there will be 5 million bacteria. To help us generalize, let's look at another example. We know if 10 to the 6 7/10 is approximately 5 million, then log base 10 of 5 million is approximately 6 7/10. Using variables, if a base a raised to an exponent y equals a given number, x, then log base a of x is the exponent y. 6.7 hours. There'll be 5 million cells by the time you go home.
That's some fast growth. Now logs make sense.
That's another problem solved.